In this post, we'll get into the exciting world of natural language processing and large language models by doing transfer learning with Hugging Face BERT, PyTorch, Lightning AI, and Google Translate. What is transfer learning? Transfer learning is a technique in machine learning in which knowledge learned from a task is reused in order to boost performance on a related task. In this case, we're using the knowledge learned from Google training BERT on its large corpus of data in order to boost performance of our classifier that will predict if a comment is clean or toxic. So how does natural language processing work? Well, the first step in natural language processing is representing the words or language by numbers. So why do we do this? We do this because computers excel at handling numbers. With numbers, we can reduce the high dimensionality of language. With numbers, we can extract features. And with numbers, we can measure semantic similarity. Semantic similarity is different than lexical similarity in that semantic similarity is how similar are the terms in their meaning, whereas lexical similarity is how similar words are in how they sound. So here are a list of some of the numeric representations of text or language, and we can see how they also evolve in terms of complexity. So term document matrix or document term matrix is a mathematical matrix that describes the frequency of terms that occur in each document. And then term frequency and inverse document frequency is then a mathematical measure of the importance of a term to a given document. And we move on to more complex representations with the latent semantic analysis. And this effectively takes the term document matrix and does linear algebra math on it, specifically single value decomposition to find relevant topics. And then the next representation, latent Dirichlet analysis. LDA deals with text in terms of understanding documents as a mixture of topics and topics as a mixture of words. And it's a probabilistic model in which words have a given probability they belong to a certain topic. So now that you know language can be represented numerically, you probably realize that neural networks can be used because we know that neural networks are good at handling numeric inputs and predicting numeric labels. So neural networks were first used in natural language processing all the way back in 1997. And some of the first neural networks were recurrent neural networks, and they were good at handling the sequence aspect of text data and the fact that text had long-range dependencies. And long-range dependencies are important because in long sentences, the subject is affected by words up until the end of the sentence, which can be a very long sequence or a long range. And gated recurrent unit is an improved version of LSTM that came out in 2014. Neural networks that learned word embeddings came out in 2013 from Google, and these were part of the Word2Vec approach and included the skipgram approach and the continuous bag of words approach. and we'll go over both of those. And so you may be asking yourself, what are word embeddings? So word embeddings are another numeric representation of language. And the concept behind word embeddings is that by mapping words to a unique list of numbers, we position it in a high dimension space. And you can think of this high dimension space like a map, but not just a 2D map or even a 3D map, but multi-dimensional. And then each word has a specific location, and similar words are closer together. This allows us to do some interesting things where we could do math with language. We can have the equation king minus man plus woman equals queen. So let's take a look at some more words in this high dimension space. This is an interactive visualization tool created by Edwin Chen of Surge AI. It's a very cool and useful tool that demonstrates the high dimensionality of embeddings, not just neural net created ones. And so we see how embeddings do a good job of showing how people's names are similar, yet distinctly different than food terms. And these are obviously all distinctly different than legal terms or sports terms. So the limitations of Word2Vec, the first neural networks that created embeddings, were, for one, it created a single embedding per word, but we know some words have multiple meanings. We call these words homographs. And Word2Vec also created word-level embeddings, but for language, we need sentence-level context. And also Word2Vec represented each word as the same vector regardless of the context it was in. So it's obvious it has its limitations understanding language. This is where transformers come in. Transformers are the big breakthrough in natural language processing. They still work with embedding, but they give context to sentences with their embeddings. The white paper that laid forth the transformer architecture is called Attention is All You Need. And it laid forth this transformer with multi-headed self-attention and encoder and decoder architecture. So what is the attention aspect in the transformer paper? Well, what this essentially means is that our transformer model will use weights to determine how much focus is given to every individual word of a sentence. And when it considers how much focus is given to every individual word, it considers the other input words in that sentence, the other input words both before and after. And that's where the bi-direction comes into play of the model that we'll be going over. And the model can also process text in parallel and focus on different parts, both in the encoder and the decoder. And this is what's known as the multi-headed attention mechanism that exists in transformers. So what is the encoder and decoder architecture? Well, at a high level, the encoder focuses on processing input and giving contextualized word embeddings. And the decoder focuses on the output sequence, and it also has a cross-attention component that's not present in the encoder, and it basically gets you from your contextualized embeddings in your input to a relevant output by bringing more context and relevance between your input and output. So why are we using BERT as opposed to GPT? After all, generative AI is all the rage right now. Well, GPT is specifically for text generation. For our problem, we only need the encoder and have no need for the decoder. BERT also predates GPT, is open source and available through Hugging Face, was trained on a large amount of data and understands context. BERT is also great at text classification. And this is because it's a bidirectional masked language model, meaning it's very good at processing language both before and after. And word order matters. We know of a lot of famous speakers in history and even fiction that change up their order of their sentence to convey special meaning. So why are we using Hugging Face? Well, Hugging Face is one of the leaders in transfer learning and open source models, and it's very easy to use. It also has what a lot of LLM contributors would consider to be the leaderboard. This is the Open Large Language Model leaderboard that's available on Hugging Face. So why are we using PyTorch? We are using PyTorch because it's a great framework for creating neural networks. It handles the abstraction that exists in networks and automatically does things like feed forward and back propagation. It will also allow us to set up and execute from checkpoints and inspect bottlenecks. It also works really well with NVIDIA CUDA GPUs. So why are we using Lightning AI? Lightning AI's PyTorch Lightning offers more flexibility for PyTorch and allows it to be scaled without sacrificing performance. So why are we using Google Translate? We're using Google Translate for our data augmentation step. Data augmentation is common in deep learning. We're using it to augment our class that we want to pay special attention to and increase that class's size. So we're going to translate our sentences from English to French and back to English. This will generate new sentences that have different word makeup but the same meaning. Our first step in building a deep learning pipeline is problem identification. In this case, our problem is we want to build a model to accurately classify toxic comments. So this is a multi-label classification data set, and our labels are toxic and other types of toxic language like insults, obscenities, threats, identity hate. To build our pipeline, we are relying on Jupyter Notebooks and Python. We have a number of libraries that we import. With a project of this magnitude and relying on this many open source libraries, environments are a must. We are utilizing Anaconda's environments because of their ease of usability. Since our dataset had a low representation of the toxic comments, we augmented those sentences by doing a back and forth translation in French to create an increased set of sentences with same meaning but different makeup. Our text data is in a neat CSV, so we can just utilize the read CSV method to read in our text columns. For our third deep learning step, the data preparation step, we begin by splitting up the data into 3 different sets: the training set, the validation set, and the test set. The training set is what we train our classifier on. The validation set is used to evaluate the model while training. And the test set is used as the final metric to evaluate the model on unseen data. For the rest of our data preparation and activities before downstream model activities, we rely on the PyTorch dataset and data loader class. To set up our dataset class, we need to properly set up three methods: the initialize, the length method, and the getItem method. The initialize points to our dataset and specifies how we access the data. You can also specify transforms like tokenization. The len method returns the dataset's length. The getItem method specifies how individual rows or our machine learning observations are accessed. Our Lightning Data Module and PyTorch Data Loader is used to create a class that will handle data processing and loading. This makes it very easy to develop dataset agnostic pipelines that share data, splits, and transformations across projects. It also allows us to scale our pipeline to higher resource-based environments when we want to productionalize this code. After we set up our Lightning Data Module and data loaders, we can instantiate it and start setting up our Lightning module. Now that we are done creating our classes for data preparation, we can begin writing the class that encompasses the model activities: model selection, model training, and hyperparameter tuning. Our Lightning module will define our deep learning network and how our inputs, our input IDs, and attention mask move in a forward manner. They move in a forward pass through the different layers. Our first layer will create the contextualized embeddings. Then these embeddings are used in the classifier layer. Finally, there is an activation function to get the output in the form of probabilities. We also specify our loss function. Our loss function is what we want to minimize during the training epochs and guide backpropagation and the gradient computation that changes the weights and biases. In this case, we are using binary cross entropy because we are dealing with a binary classification problem, whether a comment is toxic or not. We also specify our optimizer and what gets logged at the end of each training epoch. Our optimizer will handle the learning rate of our deep learner, and we could use it to handle weight decay and regularization. In this case, we're using AtomW as our optimizer. The benefit of using AtomW is that weight decay is handled outside of the gradient update. And weight decay prevents overfitting by penalizing large weights, thus discouraging the model from being too complex. At the end of our training epoch, we log our receiver operator characteristic area under the curve that we'll use for model evaluation. Now that we have set up our Lightning module class, we can set up our logging folder that will have our metrics that are generated while training. Our logging folder will have metrics that are generated at the end of the training epochs. It also has a file for us to load the model for using on unseen data or to load it from a checkpoint in case we want to pause it. Now that we have our logging folder set up, we can start training our neural network by initializing the model, trainer, and learning rate monitor and using the .fit method. When we start running our deep learning process with the .fit method, we get a warning that lets us know we are using BERT for fine-tuning a downstream process and not loading its initial weights. It also lets us know that the model has trainable parameters for both our tokenizer and our final classifier. As you can see, the tokenizer is a lot more complex, so we benefit a lot from the historical training Google has done on BERT. After each training epoch, our metrics get logged and we can access it via the TensorBoard. We load the TensorBoard through Jupyter Notebooks and access the page through another browser tab. The first plot in our TensorBoard shows us how many steps and the time that it's taken through each epoch. We'll evaluate 3 different models. One model without data augmentation, one model with 3 language augmentation, and one model with just French language augmentation. As you can see, there's a variation in step size due to the difference in size of training data. Steps per epoch is the length of the training data divided by the batch size. The next plots are the ROC curve, which plot the true positive rate against the false positive rate for each label. This is one of the most useful tools we have to evaluate our model's ability to classify the different labels. We also have a plot of our learning rate. And as you can see, all 3 models have a starting warm-up learning rate of what we specified. There is some slight deviation due to the way Adam W warms up the learning rate. Lastly are our training and validation loss curve. Our training loss curve shows a decreasing trend, which means it is learning to make better predictions. Our validation curve is trending up slightly. The loss curves are trending up for different reasons. For our data augmentation sets, this is because our data augmentation data is added to our validation set as well, and as our training goes on, our model is not generalizing well to the combined set of original and augmented data. For the non-data augmentation set, the model is not generalizing well to just the original data, which is really what we are just evaluating on. So our validation loss curves aren't the best to evaluate all 3 models against each other, which is why we just created a function to look at the confusion matrix, as well as accuracy, precision, recall, and F1 against the completely unused test set. So you can see from the confusion matrix for our base model and other evaluation metrics that there is room for improvement, especially when the categories of obscene threats and insult threats are concerned, as they do make up a fair amount of the data set. When we augmented our training data with sentences back and forth translated using Spanish, French, and German, we got significant improvement in recalling all of our toxic comments, obscenities, and insults. When we augmented our training data with just the translated sentences from French, we were more precise in what we labeled toxic, and in general, were more accurate with our predictions, but only slightly. We did lose some ability to recall insults, which may or may not be important in deciding which final classifier to use. So what do transfer learning and cryptocurrency have in common? They both heavily rely on open source communities. Python, PyTorch, sklearn, and Hugging Face are all open source technologies created by open source communities. The largest cryptocurrency networks are also open source technologies and also run by open source communities. They are both very fast growing technology sectors, and they both heavily rely on distributed computing. How will transfer learning and cryptocurrency be used together? Well, developers are already relying on LLMs to learn smart contract development like Solidity. And blockchains can ensure that the underlying training data that open source AI models are trained on are public, verifiable, and auditable. Thanks for tuning in.